So, hello students. Let us continue the algorithms for implementation of the join operations. Okay, from the previous lecture, like in the previous lecture, as we have discussed, nested loop join, right? Block nested loop join algorithm, etc. So there is another algorithm which is called as the index nested loop join algorithm. Now, when we have when we have to join two relations, so there is a joining attribute on which the joining is done, right? Now, one relation, maybe the smaller relation, has to be the tuples. The smaller in the sense that depending on the number of tuples. Okay, if there is a relation which has a smaller number of relations, you are considering as the inner relations, because there is a nested loop structure that you have to execute, right? There will be, for every tuples of the outer loop, the outer relation, okay, every tuple of the inner relation has to be executed to perform the join operation. Now, if suppose for the joining attribute, one of the relation has an index attribute, okay, it has an index file, okay, and that particular attribute is indexed. So in the sense that it has, since we have an index file on that attribute for one of the file, so what we can do, we can take advantage of the index, okay, and perform the index loop join. This algorithm is called as the index loop join. In this case, what you need to do, that the index relation, the file which has index, which has a the relation which has an index on that particular attribute, should be the inner relation, okay, because it has an index, so it becomes you can get the attributes easily without any IO operation, right? So it has to be the inner relation, because for every tuple of the outer relation, you will be calling that particular relation again and again, all tuples again and again. So it should be the inner relation, okay. Now, so it is like as we have discussed in the last class, that is, suppose if we have a relation R, which is the outer relation with m number of pages, okay. So all those tuples in those m pages in the relation R will be executed as the tuples of the outer relation, for which every tuple of the relation S, which is the inner relation, will be called, and the joining will be done on Ri and Sj, that is, every tuple of Ri, that I is a subscript, will be compared with every tuple of Sj, okay. So, and finally, if it is equal, then you write the R and S to the result, okay. So that is how the index nested loop join is performed when one of the relation has the index file on that attribute, okay. So we can take advantage of the index there. So cost of this strategy, what is the cost of performing using this index nested loop join algorithm? So as we have discussed already, that relation R has how many pages? M pages, right? So for every page, you have to perform an IO operation, because this is in the backend, right? It is not indexed on. So from there you have to retrieve every page of M pages. So there are M IOs that you have to perform, okay? So you have to perform the M number of IOs, right? So, and for every the cost of retrieving the matching the tuple S, that is from the S relation, what is that? Since we have an index file, so obviously when we are searching for an element in the index file, we have to traverse from the root to the leaf node, right? And for B plus tree, this traversal typically requires 2 to 4 IOs, okay. And for hash index, it contains 1 or 2 IOs. So depending on how you traverse, how big is the index file, you have this many number of IOs, that is either 2 to 4 or 1 to 2 IO, depending on whether you have B plus 3 index or you have a hash index. Okay. Now that is one. Next is that for every leaf node, the elements that the attribute is whether it is clustered. That is, if the particular attribute that you are matching, okay, if the index is clustered, if that index is clustered, then obviously you need very less number of IO operations, because clustered means they are in order as it is in the file. So it is basically you require hardly very few IOs depending on the number of tuples there. Okay. Now if you have a unclustered, this index is unclustered, then what will happen? That there is at worst case there is a possibility that every tuple will be there in different number of pages. Okay. So you may have to retrieve as many number of pages as there are number of tuples. So that would be the worst case in cases. Obviously in the unclustered indexes, the number of pages will be anywhere more. Okay. Even if it is not the worst case. But in case of clustered IO, that clustered index, the number of IO will be less, because all it will be in the consecutive pages. Okay, so number of pages will be very less, although it will depend on obviously on the number of tuples that you are trying to retrieve. Okay, so that is so the total cost is basically cost of performing the step number 1, that is scanning the R for m number of pages, that is m IOs, plus the cost of traversing from the root to the leaf, okay, that is either 2 to 4 or 1 to 2 depending on which type of index files it is, whether it's B plus 3 index or it is S index, and then depending on whether it is clustered or unclustered, the number of pages will vary. So the cost of the total cost is basically cost of performing the step number 1 of this algorithm plus the step number 2 of this algorithm. Okay, so that is the total cost of the join operation. Another joining algorithm is called as the sort merge join. Okay, so basic idea behind the sort merge join algorithm is to sort both the relations by the join attribute and then look for qualifying tuples R that belongs to the relation R and S belongs to the relation S by essentially merging the two relations. Okay, so this join is performed by initially sorting both the relations R and S based on those joining attributes on which you are looking to join those two relations. Okay, and then identify those attributes, actually look for the qualifying tuples where that equality condition is satisfied. Okay, so that is why it is called as the sort merge join, because you do first you do sorting on the two attributes on which you are trying to join the relation, right? Do the sorting of the both the relations and then you merge it. Okay, when you merge, obviously you look for the equality condition. Okay, that is that is merge, and then you identify those tuples which actually satisfy the criteria. Okay. So merging of the two relations can be described like, if the relations R and S are scanned in order to identify the qualifying tuple, okay, then the tuples TR in R and TS in S such that TRI is equal to TJ. Okay, so when you do the merging, you have to identify those tuples which satisfies this criteria, that is TRI and TSJ. Okay, so this can be done basically in two ways. Okay, one is basically what you can do actually, the two scan starts at the first tuple of each relation. Okay, so in the first relation you start from the first tuple and go on searching for the tuples of the next relation. Suppose you are starting from both the first tuples of the two relations, f, r and s. Okay. So for the first tuple in the relation r, you start searching for s till that tri is less than ts. Okay, and then you start in the reverse order, and then till you identify those equality condition. Okay, you go on repeating this process. That is, take one side of the tuple, one relation in the tuple, and then compare with all the other attributes of the values of the attributes of the next relation on which you are trying to join. Okay, go on comparing till it is less than this value. When it is not less than, you stop on this side, then start from the other side, the first relation, first tuple of the next relation, that is and then again compare with these attributes, and till you find that tri equal to ts, you keep on doing this. Okay, and when you identify tri and ts, you basically write this tuple to the result. Okay. So that is what has been written in the step number A and B. So for the step number A, as I told you, that is the start of the first tuple till the current tuple is less than the values of the attribute of joining attribute of the next relation. It will keep on rotating. Okay, that is keep on comparing. Okay. So advance the scan of S as long as the current S tuple is less than the current R tuple. So do it in the reverse order whenever the previous criteria is previous checking has completed. Okay. So once the tuple TR and STS having TRI equal to TSJ are found, they are joined to produce the output tuple. Okay. And then it is written to the R and S. Okay. So there may be one situation where the multiple matching can be there. Okay, for a relation, suppose for a particular for particular attribute value, when you are checking this, you have the same value in the joining attribute of the current tuple of TR and TS. Okay, in that case, you need to take the current R partition and current S partition. Okay, that you have to, when it is the same values, when it matches, multiple values matches, then you need to take this as a partition. Okay, so all tuples in S in the current S partition are scanned and output the joint tuple, that is the R comma S. Okay, so when you are having for each tuple R in the R partition and for tuples S in the current partition, because you are that one particular tuple has matched with some partition values, that is the multiple values, then you can actually output the joint tuple as R and S. Okay, depending on the number of tuples number of values in the partition which matches with that particular value. Okay, so scanning of R and S and R then resume beginning with the first tuple that follows those partitions. Okay, so after that again the next scanning starts from the next tuples after the partition. So that is how the join operation is. We have discussed 4 algorithms for the join operations, right? So after that there are also, as you know, there are set operations that can be performed on the relations. Okay, set operations like, you know, R intersection S, right? Then R cross S, then R union S, and R minus S. Okay, so these are the different set operations which are commonly performed given there are two relations, relation R and relation S, right? So intersection and cross products are actually very special cases of join, right? In which, you know, equality of all fields are considered for the intersection. When all fields are equal to one another, we take the intersection condition to identify that. Actually, we compare the equality of all conditions there, all fields there, and then those tuples which matches that, those are the intersecting tuples that we consider. And cross product is basically there is no join condition, then it becomes a cross product. Because if we don't consider the joining condition, means it is a combination of all tuple on one side to the all other tuples in the other side of the other relation. Okay, then that becomes the. So what is the technique to implement the union and the set difference? The main technique is implement the union is to eliminate the duplicates. Okay, and set difference is also implemented using the variation of the technique of duplicate elimination. Because in a set difference only you need to eliminate the relations of S if it is R minus S. That means in the set difference you need to eliminate the tuples of S which are present in the R. Okay, and that you need to eliminate, right? That is the R minus S. S obviously you need to eliminate, and those tuples which of S of which are in R, that also you need to eliminate. So basically both these conditions require elimination. Okay, only set difference is little variation of the union. Now there are two implementation algorithms for union and set difference, again based on sorting and hashing. Okay, so two implementation algorithms are used for identifying for implementation of the union operation and a set difference. Okay, one is based on sorting, another is based on hashing. So sorting for union and difference. So what is done in case of the sorting is that you sort both R and S. Okay, that is for a combination of all fields. Say in case of joining you have sorted based on one particular attribute, okay, of the relation. Based on that attribute you have sorted the relation. Here you need to sort the relations based on all the fields. Okay, so combining all the fields you need to sort R and S separately. That is first you have to do that. Okay, and then scan the sorted R and S in parallel. Scan both the relations, sort R and S in parallel, and then merge. Okay, and then eliminate the duplicates. So what happens is that when you sort both the relations on the basis of the field values, it creates the partitions based on the values of those fields. Okay, if there are some equal fields, they will appear together. Okay, so that becomes one partition. If it is not, it will appear in the sorted order in the proper location, right? After that, what you need to do, you need to merge these two relations. So when you merge this, there are likely that there will be some duplicate values, okay, duplicate tuples. So eliminate the duplicate. So when you eliminate the duplicate, you get the union of R and S. And R minus S is basically do the same, that is sort R using the combination of all fields, and similarly do sorting for S, and then scan the sorted R and S in parallel, and then merge them in such a way that only the tuples of R are written to the result. Okay, only the little different. This algorithm is little different from the previous the union algorithm for sorting. That is, you scan both the relations in parallel and then merge in such a way that only the tuples of the relation R are written into the result. Tuples of S relations are not written. Even if it comes from the R relation which is equal to the S, then also both the tuples have to be eliminated. Okay, that means only those R tuples which are in relation R but not in S has to be written to the result. Okay, So only write the results to the result, only the tuples of R, and eliminate the S tuples of S relation. So that is the criteria for merging here. So only one additional criteria that gives you the set difference algorithm for implementation of set difference algorithm. Okay. So this is how you do using the sorting, right? That you implement union and set difference using the sorting technique. Now, how to implement this union and set difference using hashing? Okay. So to implement, first let us look for implementation of union. So to implement union, you have to find out, you have to take a hash function on both relation R and S. Okay. So what will happen? It will again partition the tuples of relation R and S based on the values of the hash function, because based on the values of hash functions, the tuples will be sent to different buckets, right? So they will be sent to different buckets. So the partitions are created in terms of those buckets of relations R and S. Okay. So it will basically create a partition R and S using the hash function H. Process each partition of partition L as follows. Okay, that is what you do first. Then see, after this partitioning has been done, you need to identify only the common one for the, that is for the union only those which are either in R and S, right? And of course the which are common. So build, what you have to do, you have build an in-memory hash table with a different hash function which is identified by H2, okay? But that H2 should not be same as H function. Little bit different function you have to take, okay? And create an in-memory hash function where you will be calling those partitions. Partitions means those different buckets, the values of different buckets one by one, okay? So for the bucket of SL, you will first call suppose the one bucket or one partition of SL and create the in-memory hash table from there. Okay, and then what you do, you scan the relation R, that is a partition, because all here you will be calling one by one partition at a time. So scan the RL corresponding L partition of R. Okay, and for each tuple, probe the hash table of SL. Okay, just compare the values of SL. Okay, if the tuples is in hash table, if you find that tuple in the hash table, then you know it's a duplicate, so eliminate it. Okay, if it is otherwise, add it to the result. Okay, so that way keep on doing that till all the partitions are retrieved of both S and R relation. Okay, so L represents the subscript to call the partitions one by one. First, call a partition from S, create a in-memory hash table applying the H2 hash function on that particular partition. Then take the tuple of relation R from the RL partition of the relation R and compare it with the in-memory values. If you find it in memory, you just discard it, otherwise add to the result. Okay. If you keep on doing this, you are basically after that write out the hash table and then clear it to prepare it for the next partition. So after doing this, those results which are written, okay, in that is that table, in memory hash table. So write that in memory hash table to the result, okay, and clear the partitions for the next inputs of the partition to that particular for processing in terms of the relation, this one in terms of the partition L. Okay, so for the next partition you have to clear that particular results, because those are temporary results which are stored, right? So to implement the set difference R minus S, what you need to do the same thing like the previous one, that is create the hash tables by using the hash function H on both the relation R and S, okay, and then for each partition L, what you have to do, you have to take one partition at a time from the relation S, okay, create an in-memory hash table by using the H2 function, which is not same as the H function, little different from the H function. You have to apply that H2 function to create an in-memory hash table from the partition L of the relation S, okay, then take the partition of R relation, the L partition of R relation, okay, match the tuples, that is probe the tuples of the relation R with that of the hash table SL for the partition, okay. If the tuple is not in the hash table, it is written to the result. Since the hash table is created from the partition from which relation S, we are trying to find out R minus S, that is set difference R minus S. We don't want the tuples of S. So what you need to do, if the probe matches here, you need to that tuple should not be actually added to the hash table, okay. So if only if it is that should not be added to the result. Only if it does not match, if the tuple is not in the hash table, it does not match, the value does not match with the value in the hash table, then only you have to write the result, write it to the result, okay. That way it will only take the values of relation R but not in S, okay. So that makes the set difference here. So aggregate operations, as you know, the aggregate operations are what? Like when you have the these are the operations which are used in like the other relations. They are also used in the queries, right? There are aggregate operations that you perform. You may have to find out some maximum of some attribute, okay, right, or sum of the attribute values or count of the tuples, etc. using the aggregate operations, right? So aggregate operations can be average, AVG, minimum, max, sum, count, etc. Right? So how do we calculate or how do we implement the aggregate operation? The algorithm for this is actually to take count of the running information. Okay. Now what are those running information? Like in this table, as you can see, the corresponding aggregate operation is shown on the left hand side. The running informations are stored on the shown in the right hand side. So for sum, the running information is what? The total of the values retrieved is the running information, because we keep on calculating the total for each passing of the tuple and calculate the total, right? That is the sum. Average is, the running information is total and count, because for average we need to have both total and count, because we will be dividing total by count, right? So running informations are total and count in combination, okay? So count is the count of values retrieved. So for count average operation, we have to aggregate operation, we have to, the running information is count of values retrieved. What is the count of value retrieved? Is the running information, okay? Minimum is the smallest value retrieved, is the running information. For maximum, largest value retrieved is the running information. So these are the aggregate operations for which the running informations are this, and based on the running information, we implement the aggregate operations. Now, aggregate operations are mostly done using group by clause. You can see in the queries, you find that group by. So when you do group by, what does it mean? Suppose this particular query, as you can see, this particular query, that is select average s dot is from Sailor S, where from Sailor S group by group by S rating. Okay. Now see, there is an aggregate operation which is average. Okay. It is aggregating. It is finding the average of edges depending on what? Depending on rating. Suppose, so what it has to do? It has to identify the partitions based on rating first. Because for rating 1, the average of the edges will be done separately. For rating 2, average of the edges will be done separately. So you have to first identify those partitions based on rating, and then use the running information to perform the aggregate operation on the particular attribute on which you want the aggregate operations to be done. Okay. So to compute the averages of sailors for each rating group, we can again use the algorithm based on sorting and hashing. Okay. Because whenever there is a concept of partition being created in the tables, we can apply either sorting or hashing, because both these are techniques for partitioning the data. Okay. So sorting, whenever you sort it, you create the partitions, because when you sort, you get the same fields together, right? So you create the partitions. For hashing, using the hash function, they are sent to different buckets, so you get the partitions. So these are the two techniques for creating partitions. Now, for the sorting approach, is that for group attribute, that is the grouping attribute rating, we do the sorting. Okay. So, and then scan it again to compute the result of aggregate operation on the running information. Okay. So first you do the sorted on the sorting has to be done on the rating, because you want to create the partition on the rating, right? So on the rating attribute you need to sort the table. Okay. Then you need to use the running information to calculate the aggregate operation average for each of the partitions. Okay. That is the technique using the sorting. For hashing, that is, hash table is built on the grouping attribute. That is you need to create the hash table based on the rating here. That is, because this is the grouping attribute, right? Like whichever attribute is required for creating the partition, you have to perform either sorting on that or hashing on that. Okay. So on the grouping attribute, in this case it is rating, you need to create the hash table. So what will happen? It will create the partitions based on the hash values. Okay. So after that, the running information is used to create the aggregate operation, that is the average in this case. Okay. From all those partitions. Okay. So it is basically use of the running information on different partitions which are created either by using sorting or by using hashing. So with this we come to the end of this lecture on evaluation of relational operators. Okay. So next we will discuss the optimization algorithms, okay, in the next class. Thank you.